Hello everyone. In today's presentation we'll discuss about photodetectors. It comes under module 3 where we are going to discuss the topic and its varieties or types of photodetectors. First of all, what is photodetector? It is an opto-electric device which is used to convert the optical signal back into the electrical impulses. So normally the photodetector means it will just convert from the optical light into electrical impulses. So detector is commonly made by the semiconductor material. So here if I take the different variety or types of photodetectors, then there exist different type of semiconductor material. So what is the phenomenon, how it is going to work? So here the light is going to strike into the detector and current is produced in the external circuit which is proportional to the intensity of the incident light. It is having few advantages comparing to the any other dependent photodetectors. So it is inexpensive, it can be repeatable, volume fabrication in addition to the flexible packaging options. That is one of the how we can precise the size of the photodetectors with respect to the size of the photodetector. The main advantage of the avalanche photodiode, one of the type of photodiode, where its internal gain which is 300 times or higher than that, and it can also be used for low light level applications traditionally which can be dominated in terms of photo multiplier tube. So photodetectors, normally what we consider over here, it is made by semiconductor material and it is having few advantages. That's why we are looking for into the photodetectors. So it is having some performance criteria of the optical photodetectors. So in terms of few points which is mentioned out here, first point is sensitivity, which has to be matched to the emission spectra of the optical transmitter. So sensitivity of a photodetector which is matched in terms of with respect to the emission of optical transmitter. So that two optical detectors and the optical transmitter, they have to match each other with respect to sensitivity. And also in terms of linearity also, there is another performance point in terms of linearity, where linearity in the sense it is defined in terms of linear relationship between the intensity and the electrical signals. Then we also talk about high quantum efficiency and high spectral sensitivity. Even in terms of response time should be very fast. Stability also should be very good. In terms of temperature sensitivity also, reliability and robustness is another point which come into the picture before talking about performance of the optical detector. Of course it should have some low noise and low cost while building up of optical detectors. So let us look into the different types of photodetectors. So basically we are classified into two types of photodetectors. One is pin diode and other one is avalanche photodiode. First of all, we'll discuss first type, that is pin diode, as it is mentioned in this current slide. So pin diode means, as the name it suggests, there exist p-type and n-type semiconductor. In pin we can find it the p-type and n-type semiconductor which is separated by this I. So I is in the sense it is an intrinsic semiconductor placed between P and I, so that the structure which is developed to which is increased the frequency of the response of a photodiode. The device has a layer of n-doped intrinsic semiconductor which is covered by highly doped p-type semiconductor and the relative thick layer of n-type semiconductor. Hence this is called pin device. You can see here the pin device and its structure, p and n-type semiconductor separated by the intrinsic semiconductor, which is also shown in the different direction and which is taken from this particular the author. And you can see the images of how the pin diode looks. And I'll move further the next present particular slide. So in normal operation, a reverse bias voltage which is going to be applied into the pin diode. So what is going to happen if suppose I apply a reverse bias voltage across the device. So no free electron or hole which is going to be exist in the intrinsic region. So under reverse bias, all the electron hole pair which is existed between the junction of P and I and also I and N, which is pulled away into the reverse bias junction, so that no free electrons which can be existed in the intrinsic region, as you can find in the image. So I'll come back to the points. So incident photon having energy greater than or equal to the bandgap energy of the semiconductor material give up its energy and excite the electron from the valence band to conduction band. This is normally going to happen in the pin diode under reverse bias condition. The incident photon having energy which is greater or more than that of bandgap energy of the semiconductor material, and this energy will excite the electron from valency to conduction band, so that electrons will try to conduct from the intrinsic semiconductor region into away from the P and N regions. The high electric field which is present in the depletion region causes a photo-generated carriers to separate and be collected across the reverse bias junction, and this gives rise the current flow in an external circuit, which is known as photocurrent, as you can see here. So photocurrent, which is nothing but which is normally going to be generated as the light which is fall into the pin diode, and the electrons which existed in the intrinsic region, which will absorb the energy and it will jump into valency to conduction band. The electrons try to flow away from the intrinsic region, so that because of the reverse bias junction, so this flow of electron will form a current flow, and current is going to be called as photocurrent. The free electrons, whatever we said in terms of holes and electrons, we normally will say as photocarriers. These are the two different terms, photocurrent and photocarriers, which is keep on need to be remembered. Maybe in the exam they can ask the definitions for photocurrent and also for photocarriers. So I'll just move on the structure along with the explanation what I just mentioned with respect to pin diode. So PN junction has a space charge region at the interface of the two material types, as you can see along with the image. This region is depleted most of the carriers. The photon generated an electron hole pair in this region that moves rapidly at the drift velocity by the electric field. An electron hole pair generated outside the depletion region. They move by diffusion at a much slower rate. So junction typically reverse biased to increase the width of the depletion region, as you can find the image over here. So valency band to conduction band, the drift of photocarriers is going to be done, and once the electron move away from the valency to conduction band, though conduction band, the conduction of electrons will take place and photocarriers will generate a current, and it is called as photocurrent. So this is what explained with respect to the image. So this is what require if the question is asked for examination. So we have to explain with this image, pin diode, and also the particular graph how the electron hole pair break down, and it is trying to move away from valency to conduction band, so that photocurrent which is going to be generated. So this is how you can explain it with respect to the pin diode. And there are few equations which can also be takes place in terms of the photon flux phi, which is penetrated into the semiconductor. It will be absorbed through the material. Suppose pin is the optical power level falling on the photodetector at x equal to 0, and where px is the power level at distance x into the material. So here we are considering a photon flux phi is penetrated into the semiconductor, where P in is the optical power level falling at x equal to 0, where P of x is the power level with a distance x of the material. So small change with respect to the power level, that is dpx, in the optical power level of as this photon flux passes through the incremental distance of dx in the semiconductor, which is given by the dpx. So you can see here in the equation dpx, which is equal to minus alpha s of lambda with the p of x dx, where alpha s of lambda is the photon absorption coefficient at a wavelength lambda, where it is integrating this relation gives the level at a distance x into the material as p of x. So material with the power level, which we can take the equation in terms of p in with exponential rise of alpha s, that is photon absorption coefficient along with the distance x. So the equation to calculate the power level, optical power level, you can use the equation as p of x, which is equal to p in exponential of minus alpha s into x. So charge carriers moves at a distance. These charge carriers, either holes and electrons, if you consider these charge carriers moves a distance, we'll call it as a diffusion length. The time taken of this electron hole to recombine, which we'll call it as carrier lifetime. So we use the terms of diffusion length and carrier lifetime in terms of the electron and holes and its recombination time. So meanwhile, also we can find out the cutoff wavelength using the equation with respect to the material, whatever different variety of material which we used to develop the pin diode. Then the cutoff wavelength for the different material, which is going to be defined with respect to the last equation what we written here. The lambda, which is either lesser or equal, it should be equal also. So hc divided by eg, suppose this hc, which is going to be equal to 1.24, one of the material, divided by eg is nothing but it is represented in terms of electron volt. So this wavelength value is usually in terms of micrometer, so these are the topics which is understanding with respect to the pin diode, where you can see if the question is asked for examination, we just gone through with respect to the what is pin diode, the block diagram, and also the explanation along with the small equations whatever which is mentioned in the present slide. It need to be mentioned for the examination point. Next topic is avalanche photodiode. It is another type of optical photodetector. So it is another variation of the photodiode is the avalanche photodiode. The avalanche photodiode offers the possibility of internal gain. It is sometimes also can be referred by another name as solid state multiplier. An avalanche photodiode has diffused into p and n junction, nothing but p type, some n type semiconductors are there, just combined together to make it as diffused p-n junction with surface contouring to permit high reverse bias voltage without surface breakdown. There is no surface breakdown, but there exist of p-n junctions. So a large internal electric field leads to multiplication of the number of charge carriers through ionizing collision. So this is basically the collision of charge carriers to form as ionizing collision. The detectivity is also increased provided that the limiting noise is not from background radiations. So we'll see how the avalanche photodiode looks and what is its internal structure. So as you can see with respect to the major diagram which was given in the textbook also as per the syllabus. So you can look into this particular diagram. So it consists and p and n junctions, where we are going to say this p and n junctions there exist of n plus and p junction and p region and also p plus region, so which is separated by the depletion region called as pi region, also I intrinsic semiconductor region or the pi region. This pi region as the absorption of a photodiode, the absorption of the energy from the photodiode, which is the depletion region, it will increases as in terms of pi. So you can see the avalanche photodiode how it looks, which is in the real time how it looks was over this particular diagram, and also the graph along with this particular image which is given, that is electric field strength with respect to the different junctions. So between n plus and p region we can find the electric field strength is very high. This is what we call it as avalanche region, where the collision of carriers, photocarriers is going to be happen. So apart from that, the depletion region where the remaining portions from p to pi and p plus, these regions which we usually, this p to pi and p plus usually fall under depletion region. So let us look forward how this is going to work. Along with the diagram, we'll try to understand. So how this device operation works as following. So arriving photon pass through this very thin n plus and p region. You can see here in terms of avalanche region, the whatever the light intensity which is falled into avalanche photodiode, that energy which is falled into this thin n plus and p region, the carriers are absorbed in a pi region. The carriers, whatever that particular the energy, the charge carriers which is absorbed by the pi region, the absorption leads to the generation of the electron hole pair in this particular region. So in the pi region we can find it, the electron hole pair electron hole pair which is exist in this particular pi region. The electric field in the pi region is high enough, the field strength is high enough in the pi region, so that that electron hole pair which is going to be breakdown, or they are separated into it. The electric field across the pi region is not high enough for the charge carriers to gain enough energy for multiplication to be takes place. The electric field, however, in the n plus and p region is very high, so that the charge carriers are strongly accelerated and pick up energy, and they are trying to hitting each other, so colliding each other, and they are going to be multiplied each other. So the number of charge carriers is multiplied each other, and it is increased with the ionizing factors. So this is what call it as ionization with respect to the avalanche photodiode. So this is having few terminologies which we can mention it in terms of the responsivity and quantum efficiency, capacitance, and response time. So responsivity, it is nothing but it is a ratio of current output to the light input. High responsivity equals high receiver sensitivity. Another term is quantum efficiency, the ratio of the primary electron-hole pair created by the incident photon to the photon incident on the detector material. So this is again, the quantum efficiency is nothing but ratio of the electron-hole pair created by the photons to its photon incident on the detector material. Capacitance, however, we know depend upon the active area of the device, where there is a voltage across the devices. The response time is time needed to the photodiode to respond to the optical inputs and produce an external current.